Good afternoon, good evening, good morning, wherever you are. We are happy to restart the Holotrope seminar series again. And we are very happy to have Dmitri Kharzeev talk about a very prominent topic, about a very prominent experiment that has been taken or has been analyzed just recently. So this is a topic that Dima has been driving for years. And so we are very happy that you're starting this series off with your talk on chiral magnetic effect and the isobar run. So the stage is yours.
Okay, thank you very much, Matthias and the organizers for your kind invitation. It's a real pleasure for me to discuss this with you. And I know there are people in the virtual room who are real experts in chiral magnetic effect and did a lot of work on it. And there are also probably people who never heard of chiral magnetic effect before. And I wanted to make this talk useful for everyone. So what I decided to do is to give some very basic, very simple introduction into chiral magnetic effect first. Just tell you what it is and why I think it's interesting. And then without going into much detail, I'm not going to talk much about holography in this talk in particular, even though it was extremely important for understanding CME and strong coupling. And then I'm going to discuss the recent experimental results from RHIC, from isobar run. And I hope this would be interesting for the experts also. Okay, so let me begin. So the chiral magnetic effect has three ingredients. The first one is chirality. The second is magnetic field. And the third is chiral anomaly. So chirality in this case is chirality which is carried by chiral fermions. And in this talk, I will focus on Dirac and Weil fermions. So strictly speaking, chirality in the absence of anomaly is conserved only for Weil fermions. But dependence on the fermion mass is smooth. And so a small fermion mass is also allowed. And you can still have a chiral magnetic effect for light fermions as well. So, of course, as everyone knows, helicity in the case of quarks is projection of spin on momentum, and chirality coincides with helicity for fermions and is equal to minus helicity for antifermions. So now, what is chirality in the form of gauge fields? Well, the easiest way to think about it is to think in terms of magnetohydrodynamics. So suppose you have a medium with a very high electric conductivity. So electric field is screened, so you only have magnetic field. And if you have magnetic flux, then of course, in the absence of magnetic monopoles, it has to be, there should be a closed configuration of magnetic flux. And magnetic flux can form chiral knots. So this is trefoil. And this is a more complicated configuration, so-called Chandrasekhar Kendall configuration, which also possesses chirality. So now we can introduce a topological invariant to detect chirality of this magnetic flux configuration. It is an integral, spatial integral of A dot B, which of course is abelian Chern-Simons number, but it actually was known in magnetohydrodynamics long before under the name of magnetic helicity, and it really detects chirality of closed chiral of a chiral knot. So, for example, for right-handed trefoil, it's +1; left-handed trefoil, it's -1, and so on. So now another important ingredient of chiral magnetic effect is chiral anomaly, which actually describes the possibility of chirality transfer from fermions to gauge fields or vice versa. So what is depicted here is I have here massless fermion, which is in a magnetic field. So the fermion is charged, so it moves along closed orbits in magnetic field. And the lowest Landau level is not degenerate in chirality, and at zero momentum along magnetic field, it has strictly zero energy. So the reason it has zero energy is because you get a conservation between positive kinetic energy of motion and negative Zeeman energy of spin interaction with magnetic field. And the fact that it's zero actually follows from a particular kind of supersymmetry that Dirac-Hamiltonian has in a magnetic field. So the reason it's zero is exactly why the vacuum energy density is equal to zero in a supersymmetric theory. So now, once you have a fermion, let's say, which fermions which move along the direction of magnetic field, then these fermions will create a magnetic field rotating around them according to Maxwell equations. And once you include the back reaction of these fermions on magnetic field, what used to be just a simple homogeneous magnetic field becomes a helical magnetic field. And a helical magnetic field, of course, possesses non-zero chirality. And you can explicitly do this computation in magnetohydrodynamics and see how the currents flowing along the direction of magnetic field indeed are responsible for chiral configurations of magnetic flux. So now, chirality also plays important role in the vacuum of the standard model. So if you have a non-Abelian gauge theory, such as electroweak theory or QCD, it has infinite degeneracy, and there are states with different Chern-Simons number. So the abelian part of Chern-Simons number is already familiar to us, magnetic helicity. But then, of course, you also have a non-Abelian component as well. So all of these states have the same energy. So you have infinite degeneracy. And in 3+1 dimensions, or any even number of space-time dimensions, this is not a conserved quantity. And you have transitions between these sectors. So the simplest way to think about these topological transitions, for example, in the abelian sector, is to simply have a magnetic reconnection. So suppose I start with the right-handed trefoil. Then if I allow these lines of magnetic flux to cross, then I can transform this right-handed trefoil. I think this is actually left-handed trefoil into unknot. And this transition would really correspond to transition with a state with -1 Chern-Simons number to 0 Chern-Simons number. For the case of non-Abelian fields, it's hard, at least for me, to visualize what's really going on, but the physical meaning is still the same. So now, why do we have to be interested in this physics? Well, one reason is that this physics may be responsible for the origin of matter-antimatter asymmetry in our universe, because in 1966, Andrei Dmitrievich Sakharov formulated these three famous conditions for baryogenesis: baryon number violation, C and CP violation, and interactions out of thermal equilibrium. And actually, I found a picture of Sakharov taken around at the time when this paper was written. If you think about these transitions in the standard model, the Sphaleron transitions, then these transitions violate baryon number. They operate in the expanding universe. This means the system is out of thermal equilibrium. And so, and of course, you also have C and CP violation in the standard model. So in principle, the Sakharov conditions are satisfied. And I think it's still an open question whether or not the standard model, minimal standard model, can describe the observed baryon asymmetry. So recently we argued with Edward Shiriak and Ismail Zahed that what happens here is you actually have what we call Sphaleron freeze-out, when the rate of Sphaleron transitions becomes equal to the rate of Hubble expansion. Then Sphaleron transitions can no longer wash out baryon asymmetry, and you can get pretty close to observed baryon asymmetry of the universe. So, of course, it would be extremely exciting to study these processes in the lab. However, it appears impossible because you need to go to temperature around electroweak phase transition, because otherwise the height of this barrier is too high. And the electroweak transition temperature is about 160 GeV, and the corresponding energy density is extremely high, and we cannot create it in, for example, heavy ion collisions. However, what we can do is we can study analogous processes in another non-Abelian gauge theory of the standard model, which is QCD. So the point here is that the temperature of QCD phase transition is exactly 1,000 times lower. And this QCD plasma can be produced and is being produced and studied in the ongoing heavy ion experiments at RHIC and LHC. So, of course, unlike electroweak sphalerons, QCD sphalerons do not lead to baryon number violation, but what they do instead, as we already discussed, they induce chirality violation. And produced QCD plasma, the plasma produced in heavy ion collision, rapidly expands, which drives it out of thermal equilibrium. So again, at some point, the rate of expansion becomes equal to the Sphaleron rate. And therefore, we expect to see a substantial generation of net chirality of fluctuating sign in heavy ion collisions. So in the Big Bang, it was just a single event, and we live through this event. But in heavy ion collisions, we can do it billions of times and study what happens statistically in these little bands. So now this physics of topological transitions, I think most people believe it. So this is one of the famous movies from Derek Leinweber showing the density of FF dual, which is the time derivative of A dot B. And so you see that these transitions take place all the time. However, we have never directly detected these transitions in experiment, even though we believe that they are important for spontaneous breaking of chiral symmetry, and therefore for most of the mass of the visible universe, because most of the mass of visible universe comes from baryons, and most of the mass of baryons comes from spontaneous chiral symmetry breaking. So the question is whether we can directly observe this chirality changing transitions in experiment. And this was my personal motivation for starting to work on what has become the chiral magnetic effect. So detecting these topological transitions in the QCD plasma is not easy because they change chirality of quarks. However, quarks ultimately get confined into hadrons. And of course, chirality of quarks confined into hadrons is not something that can be detected. Therefore, to observe these chirality changing transitions, we have to find a way to convert chirality of quarks into something observable. Ultimately, the idea was that this net chirality of quarks in the presence of an external magnetic field or an angular momentum could be converted into electric dipole moment of the QCD plasma. And of course, the sign of this electric dipole moment would fluctuate because the sign of the net chirality of quarks will also fluctuate event by event. So sometimes you have an excess of right chirality, and sometimes you'll have an excess of left chirality. So now, if you want to parameterize this chirality excess, you can do it by introducing the chiral chemical potential, which is the density of chemical potentials for right-handed and left-handed quarks. But it is very important to remember that this is technically not a chiral, not a usual chemical potential, which we introduce to describe conserved quantities. So this chiral chemical potential does not correspond to a conserved chiral charge. And this is indeed what makes the chiral magnetic effect possible. So if it did correspond to a conserved chiral charge, like in the pioneering work of Alex Vilenkin, then the effect would be absent. However, we can still technically introduce this quantity, and you can think of it, for instance, as the temporal component of a background chiral gauge field. And then if you take the usual triangle diagram with one axial current and two vector currents, then you can easily find out that a corollary of chiral anomaly in this setup with the background magnetic field and a background chiral chemical potential, is that you have to generate electric current, which is equal to E squared over 2 pi squared, coefficient of chiral anomaly, times μ5 times B. So again, μ5 does not correspond to a conserved quantity, and the physical meaning of this formula is that it really describes decay of chiral charge in the presence of magnetic field into an electric current. So this current is obviously absent in Maxwell theory, because if you have a static magnetic field in Maxwell electrodynamics, you don't generate a current along it. So as I already mentioned before, this current triggers instabilities in the system of electromagnetic fields. And so it can lead to some kind of inverse turbulent flow in this system. And if you look at it as the operator relation, then there are no corrections to this coefficient here. This formula on the operator level is exact. Okay, so here is some simple mnemonic for what's going on. You have a magnetic field, you have positive and negative fermions with spins oriented either along magnetic field for positive fermions or against magnetic field for negative fermions. And then if you create some Svarion transition, which transforms all fermions into right-handed, then being right-handed for positive fermion means moving up, and for negative fermion means moving down, and so you indeed induce the current. Okay, so there were numerous first principle studies of this on the lattice. So this is one of the early papers by Arata Yamamoto. So you see that indeed you get a current which grows linearly with μ5 and linearly with magnetic field in the direction parallel to magnetic field, and perpendicular to magnetic field you do not detect anything. So this is a more recent study by Victor Braguta and collaborators. And what they did here is they looked at a system which possesses a phase transition into chirally broken phase as a function of coupling. And they measured the chiral magnetic conductivity across this chiral symmetry breaking transition. And so you can see that exactly in the region where you start developing chiral condensate, which breaks the chiral symmetry spontaneously, the chiral magnetic conductivity starts to go down. And so you can say that chiral magnetic conductivity can be used to detect this chiral symmetry breaking transition. Even though the situation is not really that simple, and for example, if you have a superfluid pion gas, then you can have anomalous currents in this system as well. So now,
Dima, may I ask a question?
Yes.
I noticed that the green curve, the chiral magnetic conductivity, is normalized to some sigma 0. Apparently, that's not set at alpha. Like, how is that normalized? Where, at what sigma 0? At what alpha is sigma 0 defined?
They defined it at some small value of the coupling. but I don't remember it what exactly.
So the curve is probably then going down again, right? Or maybe it's defined by the value that's close to.
No, I don't think it's going down again. So I forgot the definition of sigma zero, but from my conversations with Victor, I don't know if he's probably he's not here. He told me that nothing basically happens here, so it kind of stays flat and then it goes down.
Okay, thank you.
Okay, so then the chiral magnetic effect has been extensively tested in condensed matter systems, starting from our work in zirconium pentatelluride. But by now, there are many measurements in many different systems. So for a while, there was a concern about this current jetting, and indeed some of these condensed matter measurements were affected by current jetting, but this has been figured out by now. And even if you take care of all of these current jetting problems, which did appear in some of the measurements, there are many observations of chiral magnetic effect in condensed matter systems. So now that we know that chiral magnetic effect is real, so we want to use it as a tool to detect topological transitions in heavy ion collisions using the idea that outlined before. So as you know, there are two big machines which do this at present. One is RHIC at BNL, another is LHC, another is LHC at CERN, and Alice experiment is doing this. And in particular, STAR collaboration recently performed this isobar run. So these are very interesting, very recent results, and that's what I'm going to discuss in a few minutes. But first, let me just explain how does it work in heavy ion collisions. So heavy ion collisions, as you already know, produce QCD plasma, and the temperature in this QCD plasma is high enough to have a high rate of Sfariron transitions. So Chern-Simons diffusion rate is quite high. But then the colliding ions also have positive charge on them. And when you take Maxwell equations and plug into Maxwell equations this sources of electric charge, which move almost with the velocity of light, then you find that this QCD plasma is produced in an extremely strong magnetic field. So basically, this ion is surrounded by a magnetic field which rotates like this. This ion is surrounded by a field which rotates like this. And so initial magnetic field is extremely strong. It's about 100 times stronger than a field or magnetic field in a magnetar. And the magnitude of this magnetic field is completely on QCD scale. So we usually think of electromagnetic interactions as being some small corrections to strong interaction dynamics. But once your magnetic field becomes on the order of 1,000 MeV squared, then electromagnetic interactions are also extremely strong. So now this produced magnetic field, of course, rapidly decays because the largest contribution to it is given by spectators. And so that's why it rapidly falls off. And this fall off is faster at LHC with its higher energy than at RHIC. And so because of this, RHIC looks like a better place to look for this physics. And of course, there is also a lot of work that has been done by looking at the back reaction of currents on this magnetic field. And this back reaction, Faraday effect, and things like this, they significantly slow down the decay. But nevertheless, of course, magnetic field decays quite fast. Okay, so now again, once we have a magnetic field and we have a Sphaleron transition, then of course this Sphaleron transition gives us the fluctuation of electric current, and fluctuation of electric current is bound to give us fluctuating electric dipole moment, right? Because the current is just the time derivative of the electric dipole moment. So if I integrate current over time, I will get fluctuating electric dipole moment. And now, of course, what we have is we have this system of quarks, and there is an excess of positive charge, let's say, above the reaction plane, and excess of negative charge below reaction plane. And now this system is going to expand and hadronize into charged hadrons, and of course also neutral hadrons. But because electric charge is conserved throughout hadronization, this electric dipole moment, which we had in the QCD plasma, is going to get transformed into electric dipole moment that we observe for final state hadrons. And so this is the idea. We somehow found a way to convert fluctuation of topological charge into something which is directly observable in experiment. So the problem, of course, and this is really, the problem, in bold font, is that because this dipole moment keeps fluctuating, there are conventional backgrounds to this effect. And this is what makes it different from classic global parity violation in weak interactions. So in weak interactions, the sign of the asymmetry is fixed once and for all. And that's why Madame Wu could easily detect this asymmetry without worrying too much about backgrounds. And here, of course, the situation is a lot messier because we are talking about dynamical enhancement of fluctuations above some background, and we have to find a way to isolate this background. So this, of course, was understood from the very beginning. This is the paper which was written by Sergei Voloshin just, a few weeks after I submitted my paper. And he proposed an observable which actually removes most of the backgrounds. So let me explain how this observable works. So suppose I have this heavy ion collision. Suppose psi2 is the direction of reaction plane, is in azimuthal angle, and I have a hadron A and a hadron B. So for example, you can think of A as a positive hadron and B as a negative hadron. So then in an experiment, you measure this combination, which is cosine phi A plus phi B minus 2 psi 2. So this is just a simple trigonometry. And for instance, if I look at the second term here, then I expect that positive hadron will be produced on one side of the reaction plane, and negative hadron will be produced on the other side of the reaction plane. So for example, this sign will be positive and this sign will be negative, or another way around, this could be negative and this would be positive, but the sign of this product is always negative if A and B are positive and negative hadrons. And so this is exactly what we want to look at. However, Sergei proposed this quantity, which is really the difference of sine, sine, and cosine, cosine. And the reason he did it, because he understood that there would be a background in this correlation. And so by subtracting from this background, this product of cosines, you remove background which does not depend on the orientation of reaction plane. So basically, this difference here is the difference of fluctuations in reaction plane and fluctuations out of reaction plane. So both contain backgrounds, and if there is no dynamical enhancement, let's say perpendicular to reaction plane, then these backgrounds cancel each other. If there is some enhancement along magnetic field, then you would be able to see it here. So it was understood from the very beginning that these backgrounds will be there, and these observables are designed to eliminate at least part of this background. Unfortunately, not all, as I will explain later. Okay, so then a few years later, Starr presented the first measurement of this correlator. So experimentalists sometimes call it gamma correlator. And you see that for same charge and opposite charge, this cosine has expected sign. There is a big difference. And none of the Monte Carlos, which were available back then, did not describe this difference. So this was considered as kind of a first evidence for the CME. So now, before we go to isobars, I would like to emphasize one thing, which again was understood already in the first paper, that both signal and background in these observables scale as inverse multiplicity. So this I just copied from my paper from 2004. There is a clear scaling of signal with 1 over hadron multiplicity. And there is a similar formula in Sergei's paper. So everyone from the very beginning understood that all of these observables will exhibit this 1 over multiplicity scaling. So now come the isobars. So what is the idea of isobars? So the idea behind the isobar run was to really nail down the background contribution and eliminate it. And the idea was that there are some backgrounds which actually are not eliminated in this gamma observable. And one such background comes from resonance decays. So for example, if you have some resonance and the emission of this resonance is not azimuthally symmetric due to so-called elliptic flow, then because electric charge is conserved in the decay of resonances, these resonances in principle can contribute to gamma. So elliptic flow somehow messes up this background subtraction. But elliptic flow is driven by geometry of the collision. So this is what was established through hydrodynamic simulations. And the idea of isobars was to use the nuclei which have the same mass number, and therefore it was assumed the same shape. And if they have the same shape, then elliptic flow and multiplicity and everything else will be identical. And so background will be the same. However, isobars have different number of protons, different electric charge. So magnetic field is different, and there will be a change in signal. So it's a beautiful idea, and it was a truly heroic effort, not just by star experimentalists, but also by accelerator people to really, develop these sources of ruthenium, zirconium. The run was extremely successful. So you can see that projection was made with 400 million events, but in reality, 3.8 billion events were recorded. So I think it's the cleanest, largest sample of heavy ion collisions that we ever had in history. And so, from experimental side, it was really a stunning success, this isobar run. However, to make a conclusion based on the isobar results appears to be much more complicated than originally foreseen. And the problem is that even though these isobars do have the same mass number, they have somewhat different shape. And this difference in shape is significant to give you a different shape of multiplicity distribution. And if you have a multiplicity distribution of different shape, and you make the same centrality cut, for example, 20 to 50%, then in this centrality cut, the multiplicities of hadrons appear different. So this is now experimental fact. Okay, but before I discuss the effects of this multiplicity difference, let me just tell you what STAR collaboration released at face value. So the release was made on August 31st. So here is the corresponding archive paper. And the main statement in the abstract of this paper is that no CME signature that satisfies the predefined criteria, so this is very important condition here, has been observed in isobar collisions in the blind analysis. Okay, so here I have to explain that the way this analysis was done. This analysis was the first blind analysis in heavy ion physics. So people who analyzed the data did not know whether they were looking at ruthenium, ruthenium, or zirconium, zirconium. Accelerated people switched from ruthenium, ruthenium to zirconium, zirconium, and so the run was divided into subruns. And these subruns were separately analyzed, but people who analyzed the events did not know what they were analyzing. And also, it was demanded that all criteria would be predefined. And in particular, the predefined criterion was that ruthenium, ruthenium to zirconium, zirconium would be larger than 1 if CME is there, because magnetic field in ruthenium, ruthenium is larger than in zirconium, zirconium, or CME would be absent if the ruthenium, ruthenium to zirconium, zirconium were equal to 1. So if magnetic field contributes, everyone expected this ratio to be above 1. If CME is completely absent and everything is background, this ratio would be equal to 1. But what has been observed is that all of these ratios, as you can see, actually appear to be less than 1. And because the predefined criterion for CME was that this ratio would be larger than 1, and the ratio is less than 1, it was declared that no CME signature has been observed that satisfies the predefined criteria. So technically, what they said was completely consistent with this predefined criteria for the blind analysis. However, if you look at this a little bit closer, you get puzzled because the ratio is less than 1. The deviation from 1 is statistically significant, in particular for this gamma correlators that I told you about before. And this ratio being less than 1 was not predicted by any theory, CME or not. So no one predicted this ratio to be less than 1. So what is going on? Well, the point is that the predefined criteria, as I already mentioned before, assume that multiplicities in ruthenium-ruthenium and zirconium-zirconium collisions in the same cross-section cuts are the same. So is this criterion supported by the data? Well, of course, the ratios of multiplicities have been directly measured. So here is this ratio from Star paper, and you can see that multiplicities are very significantly different in ruthenium-ruthenium and zirconium-zirconium. As I explained, and due to the difference in the shape of ruthenium and zirconium. And this is not a small effect we are talking about. So this is the range that was used in the analysis. And you can see that there is a very significant difference in multiplicity. And now we know that both signal and background scale is 1 over multiplicity. And therefore, if I look at this ruthenium-ruthenium to zirconium-zirconium, of course, I have to correct for this difference in multiplicity. And this is not part of predefined criteria. So predefined criteria assumed that these multiplicities would be the same. So Star, of course, understood all this. And so if you read their paper carefully, then you find the following discussion. They say that the value of delta gamma, so this is this difference of gamma correlators between ruthenium and zirconium, scales with the inverse of multiplicity. And therefore, it may be considered that the proper baseline for this delta gamma between the two isobars is the ratio of the inverse multiplicities of the two systems. However, they say analysis with respect to this baseline is not documented in the pre-blinding procedures of the blind analysis, so is not reported as part of the blind analysis. However, they did include this inverse multiplicity ratio as the rightmost point in their summary plot, which is this figure 27, which I show here. So this is the ratio of observed multiplicities, which I think most, well, actually, I have yet to meet a person who would believe that this is not the right baseline. Everyone I talk to believes that this is the right baseline. I mean, you may argue that maybe, this is not exact baseline, and maybe one has to correct for, some other small effects, but they are small effects. So the main difference is really this inverse multiplicity scaling. And now, of course, since they put this ratio right here, it's clear that this is the appropriate baseline, at least in a very good approximation. And if you take this baseline instead of 1 for this gamma correlators, then you see that this ratio of gamma correlators is somewhat above this baseline. Of course, I wouldn't claim, an observation of the effect based on this because, the statistical significance is small. So there are different methods which they use to analyze this gamma. And so statistical significance of this kind of varies between 1 sigma and 4 sigma. But definitely, if you look at this plot, you would never conclude that, it rules out CME. And so I think that detailed analysis is needed. I know it is ongoing. So we participate in it on the theory side. I know that experimentalists are doing the same. So there could be some kind of small variations in this baseline, a little bit above, which would kind of eliminate the evidence, or maybe a little below, which could make it stronger. So, stay tuned. The jury is still out on the implications of isobar run. And in particular, quite soon, less than in 2 weeks from now, we will have a conference at Stony Brook, which will, a big part of this conference will be discussion of this issue. So if you are interested, on November 1st, there will be 5 presentations from STAR collaboration and a discussion of baseline. So this is sort of unfolding story. Okay. So now, before summarizing, let me just mention a few more recent developments. So one thing which I would like to point out is that there is some reason to expect that CME may be enhanced at lower collision energy. And I know that Matthias and collaborators recently arrived at a similar conclusion. And our motivation for this was the existence of this critical point in the phase diagram of QCD, which one may reach at lower collision energy. And we found that this Chern-Simons fluctuations can be strongly enhanced near the critical point. So we did some quantum simulations to compute Chern-Simons fluctuations rate together with Kazuki and Yuta. And of course, QCD is out of reach for this quantum simulations. But we found a much simpler model, which has a similar critical point, which is a massive Schwinger model near theta angle equals to pi. So the existence of a critical point in this model was demonstrated a long time ago by Coleman. So basically, you get for massive case, you get the phases corresponding to orientation of background electric field, like ferroelectric phases. For very small mass of fermions, you get screened phase, electric field is screened. And then when you increase mass to coupling, at some point you hit this critical point where you have a second order phase transition. And this critical value of M over G is about 0.33. So this is effective potential of the model, and we just computed using this digital quantum simulations the rate of Chern-Simons diffusion, and found that right in the vicinity of this critical point, there is a sharp peak in Chern-Simons fluctuations. So if low energy heavy ion collisions indeed bring us to the vicinity of this critical point, and this is the idea of this energy scan, then there will be a sharp peak in topological fluctuations, which would be reflected in CME observables as well. We also did quantum simulations of the CME current itself. And last thing which I would like to mention is our recent work with Adrian Floyer, who is an excellent postdoc at Stony Brook, where we also looked at real-time dynamics of these currents. So we have pulsed electric field, which produces fermion, anti-fermion pairs. And of course, in this process, let's say a positron is produced and it's entangled with an electron. And on one hand, one can simply use formulas of statistical physics and compute Gibbs entropy of a system of electrons and fermions produced. Or one can, let's say, take a trace over all electrons and compute the entanglement entropy of positrons with electrons. And so what we found in this paper is that these two entropies exactly coincide. And so one can think of this kind of entanglement as being a microscopic origin of Gibbs entropy. And I think it's quite interesting to think about this connection. So we also found that entanglement entropy can be reconstructed from the moments of multiplicity distribution. And we actually did some literature search and found that a very similar formula was first derived for evaluating entanglement entropy from shot noise in quantum point contacts. So it has some application for superconducting qubits. And this is an asymptotic formula, and we found a good way to resum this series using Padel methods. Okay, so last thing I would like to mention is that if you have a short pulse, then basically the entropy that you produce looks approximately thermal. And so we speculate that perhaps the entanglement could be the origin of fast equilibration that we seem to observe in high energy hadron and heavy ion collisions. But it's really a speculation at this point. Okay, so I just have 3 minutes left, so let me summarize. So the first point I want to make is that chiral magnetic effect and related quantum transport phenomena are firmly established both theoretically and experimentally in condensed matter physics. And they are direct probes of topology of gauge fields. So I did not have time to talk about related quantum phenomena, and this is extremely, exciting topic. And many of you did some really pioneering work on it. So I just limited myself to CME. CME in heavy ion collisions is a unique opportunity to observe in the lab topological fluctuations in QCD. And the recent isobar run has been extremely successful. We have unprecedented amount of precise data. And the careful analysis of this data, including the baseline differences between the isobars, is imperative and requires a concerted effort of both experimentalists and theorists. Early estimates, including the inverse multiplicity baseline, suggest the presence of CME at 1 to 4 sigma level. But as I said, this really has to be refined. So this is it. Thank you very much for your attention, and I will be happy to answer your questions.
Thank you very much, Dima. That was a very nice and comprehensive talk. I have a lot of questions, but I will step back and allow the audience to start. Or if the audience, Martin, please go ahead. Martin, you're muted. At least I don't hear you.
Okay, sorry. Can you hear me?
Now I hear you very quietly.
Okay.
It's getting better.
Getting? Okay, good.
Yeah.
So I've got a question regarding this 1 to 4 sigma level. So
Yes.
this is of course big. Like 4 sigma would be nice, 1 sigma would be can go really away. So how does this come about? This huge difference between 1 and 4 sigma.
Okay, so they have different working groups within STAR, which used different methods for measuring this gamma correlators. And the strongest sort of 4 sigma points comes from some very sophisticated method of using sub-events and so on. And so they claim that this is kind of the most advanced method, which eliminates some background, because I think what they do is they reconstruct reaction plane not only by looking at the azimuthal distribution of hadrons at mid-rapidity, but also looking at spectators produced in 0-degree colorimeters. And then the idea is that the signal would be oriented relative to spectators because they determine the direction of magnetic field. Background would be oriented relative to this mid-rapidity hadrons because they determine V2 on which background depends. So this is kind of a very sophisticated method. These are different methods. And whether you can just pick this point and declare victory and say I have a 4 sigma evidence, maybe it's too early to do that before you understand in very detail what was actually done here. And so this is exactly the topic of our forthcoming discussion at this conference. So now, if you just take it at face value, you can just say, well, some methods give you something consistent with 1, I mean, this new 1, and some methods give you something which would be, 2 sigma, 3 sigma, or maybe even 4 sigma.
Okay, thanks.
Mm-hmm.
Maybe I may jump in there and ask a question about the gamma observables. They seem to be distinct from, or their ratios seem to be distinctly smaller than the green variables, like the kappas that are defined in a different way in the case.
Yes. So to be honest with you, I'm not yet prepared to describe what these kappas are. So these are different ways of observables, which have to do with I think invariant mass distributions of pi and pairs, but I mean, this is much less clear to me, what the meaning of it is. Okay. So I'm not prepared to discuss these kappa observables yet, but I certainly hope to learn everything about them in November.
Yeah, it would be nice if they turned out to be just more sensitive, and that's the reason. If there's a reason why they seem to be strong,
yeah,
showing
so
stronger.
The working groups that propose them. So you see, there's this group 1, group 2. So there are different working groups. So there are 4 working groups indicated here, and so there are 2 independent working groups working on this kappas, and obviously. the reason they developed this kappas is they are convinced that these kappas are more sensitive than gammas, right? But I really have to understand better the physics of these kappas before I can comment. But at face value, I mean, it looks like this kappas indeed, if this is the right baseline for kappa as well, then it would be, a very strong indication. But, I'm not ready to claim this.
I'm glad that I'm not the only one who read that paper and didn't understand the kappas. I mean, I barely understood the gammas. So, okay. Thanks for commenting on it.
Mm-hmm.
Any other questions? Carl.
Yeah, hi.
Oh, hi, Carl.
Does it? Yeah, hi. Okay. Yeah. Sorry, I had a stressful day. I came in late a little bit and had my sorry. Yeah. I have a question and a comment. Probably I start with the comment.
Mm-hmm.
I would strongly recommend the experimentalists to hire some string theorists who help them to write papers, because after a 3 years major effort, spending millions and millions of dollars, knowing that there is an issue about the baseline, to write this abstract is and because when I heard the first talk about this, I was really disappointed, because when I saw the paper and saying in the paper, there's no signature of CME, knowing that there are issues with the baseline.
Yeah, no, I have to agree with you. And when I point this out, they say, well, it's written that satisfies the predefined criteria, but of course, no one outside this community would not know what the predefined criteria are. Right?
But apparently, at the time of writing, they were already aware of this issue with the scaling.
Yes. Yeah. So this, for example, this thing here is from this paper.
Paper. But it's so buried that I read the paper, and even in the first, after that, I thought I could not really. So just as a comment, probably papers can be written.
I share your sentiments. Of course. Yeah.
And then I have a more detailed question, and I'm not sure because it's so what I remember from this heavy ion collisions is that what I heard is you take multiplicity actually as a proxy for centrality. How do you know how they can distinguish centrality and multiplicity?
Okay. This I actually know very well, because I did these computations of myself, and I can explain how this works. So what you do is you compute the d sigma differential cross section d sigma over dn, where n is multiplicity. So you compute the shape of inelastic cross section as a function of multiplicity, right? Because you have a multiplicity distribution. So you have a certain probability to detect a certain multiplicity in your central detector, right? And then when you compute this, it generally has this kind of a shape, kind of horseback shape. And the shape of this distribution is completely determined by the shape of the nuclei, which go into your computation. So now, when they do this plots, what they do is they take this curve and then they slice it. Let's say they take, let's say 20% most central collisions, which would be on the right of this horseback, right? And then they take, let's say, 20 to 50%, and then the rest. So they slice this curve into different slices, and then they take 20 to 50% slice. But because the shape of these curves is different, obviously, if you take the same 20 to 50% slice, it's going to give you a different multiplicity in ruthenium and zirconium. And so this is why this multiplicities in this 20 to 50% centrality cut are different.
Okay. Okay.
So alternatively, what they could have done, instead of sort of slicing these distributions which have different shape, they could simply compare these gammas at the same measured multiplicity, right?
Right. Right.
And this, I think, would be a much better way, but this is sort of approximately equivalent to this. However, if you slice it in multiplicity, then instead of having just one baseline, I mean, you could really do it as a function of multiplicity, and then you can look at these ratios for different multiplicities. So I proposed this to Star people, and they told me that they actually have this data, and this data show that all of these gamma ratios as a function of multiplicity are systematically above baseline for all multiplicities.
Mm-hmm.
But this is one thing that they should definitely do and publish, because I mean, you really have to compare it at the same multiplicity. You cannot just compare things with different multiplicities.
Mm-hmm. And so since this is also the holotube, I would like to ask from your point of view, what is, say, from holography? You have also used holography in your research. So what sort of questions pertinent to this result, so to the future for CME, which are still out there, which you think could be addressed with a
I think, yes. So, as I briefly mentioned at the beginning, so holography played extremely important role for understanding what happens to this strong coupling. And I think holography really led to this flourishing activity at the intersection of hydrodynamics and anomalies, right? Because once you know that the effect persists at strong coupling, you know that appropriate effective theory at strong coupling is hydrodynamics. So this is how this whole thing started. So what I personally see as a next frontier for holography is the study of real-time dynamics. So what happens out of equilibrium, because, for example, for CME, I know that if you compute this chiral magnetic response at weak coupling, which we did with Harman long time ago, and at strong coupling, which several people did, there is a huge difference. And I think understanding real-time response using holography as a function of coupling, I think would be extremely interesting. That's just my personal view. And we also have, now we have, at least for some simple models, we also know how to do it using quantum simulations.
Right.
And so I think this could be a very interesting direction.
Okay, thank you.
Thanks for the questions. Any more questions? Since you mentioned the entanglement entropy, maybe that is a good point to tie back into holography explorations as well.
Oh, yes. Oh, thank you for mentioning this, because yes, actually, yeah. So this is another thing where holography would be extremely interesting to look. So I know that people studied this Schwinger pair production and strong coupling, right, and identified geometry responsible for entanglement. And so I think it would be extremely interesting to see whether this correspondence between entanglement entropy between the produced pairs and the Gibbs entropy, holds at all values of the coupling, what is kind of geometrical origin of this. So this is, so this, and this is also the real-time chiral magnetic current in 1+1, right? So I think this is indeed where holography would be very, very valuable.
The result that you showed, where the Gibbs entropy is equal to the entanglement entropy, does that happen in a regime where that is expected? So in infrared, when the entanglement entropy is probing the infrared, for example, in thermal states, then we would expect this to happen, right? That because, for example, one way would be to make the entanglement region just as large as the system itself, and then the entanglement entropy approaches the thermal entropy. So is this the case in your calculation, or?
Well, it's the system is not thermal, right? So basically what we do is we consider a pulse of electric field. So we can get analytical answers, as was known for a long time for the case of Soter pulse. But, in general, I believe it's true for any pulse. It's just that we don't have analytic answers, but we check numerically for a number of pulses. And if you have, let's say, this time-dependent pulse, then it produces, a system of the C plus and minus pairs. And for all of these pulses, we observe that this equality holds. That Gibbs entropy of this system is equal to entanglement entropy between fermions and antifermions.
And what was the entanglement region? Is there any notion of that?
No, entanglement entropy in our case, so there is no region. So what we did is, you have, let's say, right moving electron, right, and left moving positron. So what we did, we just traced over, let's say, left moving positrons, and then we have only a density matrix of right moving electrons. And then we computed entanglement entropy for this mixed density matrix of right moving electrons. So entanglement entropy usually, of course, is defined, by introducing some region in space, right? But you can also define it this way.
This is optional. Yeah, I mean, this is like how to separate the states in the Hilbert space. That's
exactly.
to us.
So you basically have the sort of product of right movers and left movers, and then you trace over left movers.
Okay, great. Thank you so much. Any last questions? I mean, I'm just allowing people to have some time. If not, then we can stop the recording. And so first of all, officially, thank you again, Dima, for
thank you so much
talk and for the very interesting discussion. Thank you everyone for the questions, and see you next time.